Hi, here we've got a short video over inverse functions, and specifically we're going to look at how to identify inverses. We're going to look at how to identify inverses from a table, a graph, and from the equations themselves. So here we've got the definition of inverse function, and so I'm going to read this. It's kind of a wordy definition. Don't let this confuse you, but we're going to give you the formal definition from this website down here, and then I'm going to kind of show you how this fleshes itself out. An inverse function is a function that undoes the action of another function. A function g is the inverse of a function f whenever if y equals f of x, then then x equals g of y. Meaning, if you think about our function notation, if I put x into my f function and the output is a y, well, then I can put a y into my g function and the output is an x. They're like opposites, okay? In other words, applying f and then g is the same thing as doing nothing at all. We can write this in terms of the composition of f and g as g of f of x equals f of g of x equals x. Meaning if you put one function inside another function, that's the same as putting the second function inside of the first function. And both of those are kind of undo each other and is the same thing as just having the x itself. So these are examples of inverse functions. We're actually going to explore on the next slide a little bit more about how you can tell they're inverses just by looking at them. So let's go ahead and look at that. So here what we have is we have equations, tables, and graphs. And I've got the same functions f and g. I show them as equations, I show them as tables, f and g, and I show them as graphs. Here's f in red, and here's g in blue. And let's look at how to identify that these are inverses from each of these three representations. So as I look at this, I'm going to start with the tables. I think that's the most straightforward. We had mentioned how they're kind of opposites. And I don't know if you can pull this out of that definition from the previous slide, but here, notice how we have the ordered pair 1, 7, but on the inverse, the ordered pair is 7, 1. If I interchange x and y, and that point is on the other graph, then it's inverses. And if that's true for all points, I should say. Notice we have the ordered pair 2, 9, and that becomes 9, 2. And then lastly, the ordered pair 3, 11 would become the ordered pair 11, 3. Since each of these, since each point on the original function has a corresponding point on the inverse function, where the x and y are just interchanged, we know these are inverses. Now look at how this kind of manifests itself on the graph. Let me kind of be color-coded here. So we have our f function shown in red, so I'll kind of put that in red, and then we have the g function shown in blue. Now if I look at my point, we have the point 1, 7 on our original, and there's the point on the inverse 7, 1, which we've shown in the table, okay? And then the ordered pair 2, 9 corresponds to the point 9, 2 on the inverse. See, each point on the original function has a point on the inverse where the x and y are interchanged. Same thing with 3, 11 and 11, 3. And so what this is going to cause whenever we change x and y is it means that your function is going to be reflected. If I were to draw like an imaginary line kind of diagonally through the center of my graph, it means that our inverse is always going to be reflected over this line. And this line is the linear function y equals x, or y equals 1x plus 0. It's a line with a slope of 1 and a y-intercept of 0. I know I didn't draw it super well, but note that every point over here, if you treated this like a mirror, it would reflect to that point on the inverse. If I had, I'll try to draw some random thing. If I had some random function right here, then the inverse would be reflected over it. We're going to kind of talk more about situations like this in a later video. But for now, just know that in a graph, the two functions are reflected over y equals x. That's how you know they're inverses. Now let's come back to the equations. This is the part that might be the most complicated, but we'll see. So if you remember, what it said on the definition is that f of g of x equals g of f of x equals x. That was one thing that we said about our definition. If these functions are inverses, then this statement is true. And so we need to have a basic understanding of function composition before we look at this next part. And if you don't know that, go back and watch my video on function composition. But right here, what I'm going to do is let's first take the g function and substitute into the f function. So if I were to take, I'm going to do f of, I'll try to be color-coded here, g of x. And so what that is our f of x function is the equation 2x plus 5. But instead of x, we're substituting g of x in. And so what I'm going to do is I'm going to take my g of x function, which is x minus 5 over 2, and substitute it in. Now if I do this and I do this math right here, here we see, I could distribute first that 2 if you want to, but I see we're multiplying by 2 and dividing by 2, so those are just kind of like inverse operations. And so then what you're left with is x minus 5 plus 5. Okay? You can see x minus 5 plus 5. Well, the minus 5 and the plus 5, those are additive inverses, so they can just kind of cancel each other out, and it leaves you with x. Okay? In other words, f of g of x is x. If you substitute one function into the other function, the result should just be x. And if it is, you know they're inverses. Now, let's kind of go the opposite direction. Let's do g of f of x, okay? Because normally, whenever you do a function composition one way, it's not the same if you do it the other way. It's not commutative, but with inverses it is. So this should result in x as well. So now I'm going to start with my g of x function, which we have here in blue. So it's x minus 5 over 2. But instead of x, what we're doing is we're substituting in my f of x function right there. You can see I just took that f of x function and substituted in for x in the g function. And now let's simplify. In my numerator, I have 5 and a minus 5. And so those will add to 0. And then I have 2x over 2. And those will divide to 1. And it just leaves you with the x like we thought. So that's kind of the moral of our story. And then to recap real quick, from tables to identify inverses, you see that every point on the original has a corresponding point on the inverse where x and y are interchanged. 1, 7 becomes 7, 1, so on and so forth. On a graph, each of those points, how it looks is, if I take each of those points and the point on the inverse, it's like they're reflected over this imaginary line of y equals x. And then what we tell from equations is if I take one function and substitute it into another function with function composition, the result is going to be just x every time. Those functions undo each other.